So today we talk about mass first, and then we'll move on to density. So as we just talked about in our question of the day, mass is the amount of matter in an object. So how much matter is there in an object? And we know in the physical world, all matter takes up space and has mass. That's the definition of matter. So your desk has volume, takes up a certain amount of space, it also has mass. How about water in a water bottle? Does it have volume?
Yes. Yeah.
Does it have mass?
Yeah.
How about air in this room?
No mass.
Does it take up space?
Yes.
Does it have mass?
Yes.
Your yeses or no?
Yeah.
It does. So even a gas, even the air in this room, even though its mass is relatively low, it does have mass. And in physics, we talk about this concept of the law of conservation of energy and matter. This law says that matter cannot be created, cannot be, what do you think I'm going to say next? Destroyed. Then what can happen to it? It can be changed. It can be transformed. Well, does that make? What if I take yesterday in my house we had a fire in our fireplace, and we burned some logs. Well, didn't I destroy the wood that I put in my fireplace? It was gone. So did I destroy the matter of that log? No, I changed it. I transformed it. Some of it remained in my fireplace as ash, but the majority of the mass of that log, what happened to it? Was released in the smoke from the fire, and carbon dioxide, carbon monoxide, and water vapor, and other materials that were leaving the log. Okay, those were in the wood to begin with. They were just transformed.
Why do you put the wood?
Because it's not an animal. So when we measure the mass of an object, the base unit in the metric system is grams. So we use typically kilograms, grams, and milligrams, the most commonly used units for sort of general everyday purposes. So a kilogram is more than 2 pounds, about 2.2 pounds. So we're familiar with pounds. So a kilogram is a couple pounds. A gram is about like the mass of like a pencil cap. That's about maybe a gram or so, just to give us the conception of it. A milligram is a very small amount. Obviously, if it's milli, it tells us it's 1/100th of a gram. Where do you typically see milligrams? You might like to see this if you take a vitamin. You look at nutritional facts. Nutrients are typically given, like if you take an Advil, one Advil is like 200 milligrams of Advil. That's how much of the active medicine is in that capsule or whatever. So that's where you often see milligrams. So to measure mass, we can use a couple different tools. So one tool that's often used is a triple beam balance. You guys ever use these in elementary school? Oh, you use like the balancing one? So you put little weights on the other? Yeah, well that works on the very same principles. But this one's a little bit different. So on the triple beam balance, you have the place where you place your objects called the pan. You're going to label this diagram. Now, when there's nothing on the pan and all of these riders are set at 0, what should happen? The pointer lines up, there's a little mark, and it lines up with that mark. Then we say it's 0. These things that slide back and forth are called the riders. Now, if you have nothing on the pan, everything's set at 0, but this mark is not lining up, you have a little knob underneath the pan that you could turn forward or backward to adjust that. Like right now, this one, the pointer is a little bit below the 0 mark, so I could turn this 0 knob backward, and it should raise this up a bit. And this helps you to be accurate in your measurement. You always want to make sure the balance is 0. I think I need to go a little bit more. And now it should be about there. Is it on 0, Devin?
Yeah.
Okay, so I zeroed it out. Now I know when I measure the mass of an object on there, it is going to be accurate. So once you put your object on the pan of the balance, you start moving the riders. You'll notice when I put the pen on the pan, the pointer went up. So what am I going to do? Move these riders until it goes back to 0. Now, when I slid the smallest one up, where is it? Down too far. What do I have to do? Put it back up until it zeroes out, and then I read those riders to figure it out. Now, if I put something larger on the pan, I can slide the little one all the way up, and it doesn't even move. What do? I go back down, and now I can slide the medium one. Still doesn't go down. Now I need to use the larger one. Okay, when it goes all the way down, what do? Go back one, and now I start with the medium one. Once it goes down, what do? Go back one. Then I go with the lowest one, the smallest one, and eventually it'll balance out. How do I know the mass of my clipboard then? I add up each rider. So this one is on 300, the big one. The medium one is at 60. And then the smallest one is about 3 or so. All right, let's pretend it's balanced. It's 363.1. Add them all up. That's how many grams of mass my clipboard has. Does anyone's doctor's office, back when I was a kid, in the doctor's office, they had one of these.
Yeah, I know.
Oh, really?
Yeah.
Okay.
No, to measure.
Yeah, they just know the little, the infant one often has it. They also have like a stand-on one with the, okay, here? Like my kids' doctors, they have just a digital. So that works on the same principle. All right. Now we also have a digital balance. You guys have used this before. We have in the back. So a digital balance is really simple to use. It still has a pan, but instead of moving riders, it has a digital display that tells you the mass of whatever you put on it. It still has a 0 button. You want to make sure that when nothing is on the pan, that button has been 0. But you also can use that 0 button. Like, how would I measure? Say I wanted to know, I put some liquid, I wanted to measure the mass of some liquid.
You have to measure the container when it's empty.
All right, Will, what do I do?
You measure the container with the liquid, and then or without the liquid. Then you measure the container with the liquid, and then you subtract the container with the liquid.
Correct. If I'm using a triple beam balance, correct. What if I'm using that digital balance, Caitlin?
You can put the thing on the pan and like let it weigh it, but then press the 0 button and then add
And then what does the reading tell me? Only the mass of the water. Correct. All right. So if I'm looking at a triple beam balance and I see the riders in this position, raise your hand and tell me, what is the mass of this object? What's the mass, Max? Let's pretend they're right on these marks.
175.
Yep. Veggie burgers? Falafel balls? Pieces of pita bread? Great.
Next nuggets.
All right, how about this one? Danielle, 328 grams.
Peanuts. Wait, peanuts. I missed it.
All right.
Mr. Peanut.
Well, mass and weight, like I was talking about before, technically they are not the same thing. We often use the words interchangeably, but there's a difference between them. So mass, as we talked about, is basically how much stuff, how much matter is in this object. Yeah. It does not change with location. If I took this cylinder of solid gold with me to the top of Mount Everest, would its mass be any different?
Yes. No. No. Wait, not
No.
as mass.
No. If I took it to Jupiter, would its mass change at all?
Yes. It's gravity. Yes, because the does not change
No.
with location.
Listen, we got to use our words carefully. Its mass would not change at all. It's still made of the same molecules, in the same size, same shape. Its mass would be the same.
But the gravity is different.
Right. So weight. Now let's talk about weight. How can we define weight in a way that's slightly different from mass?
Weight is the how heavy you are.
Now we're getting somewhere. Sort of, close. Weight is the pull of gravity on a specific mass. So yeah, weight is determined by two factors. The force of gravity pulling on an object and that object's mass. Now we don't really need to get into the details, but we multiply, this is a generalized formula, the force of gravity times the mass of the object, we get its weight. So we sort of use the words interchangeably, mass and weight. Because why do we do that?
Because we just are used to the same gravity.
Because we all basically live under the same force of gravity here on Earth, right? So we kind of can use the terms interchangeably. But when we start thinking about different planets, different situations in which the force of gravity is different, then we have to be more careful in our language. So we're going to be using mass. So the units that are used technically for weight is a unit of force called newtons. It's the force of gravity pulling on an object. So gravity depends on the size of the object. The larger the object, or the more mass it has, the more gravity it has. It's also dependent, you think on a macro scale, on how far away from the planet or the object something is. The farther away from the center of the Earth go, what happens to the force of gravity? It's lower and lower. No. So, if you were able to take a super accurate scale and measure your weight at the bottom of a very deep valley, and then at the top of the highest peak of Mount Everest, you would see a difference. Now, your mass would be the same in both places, right? Because you didn't lose any molecules from your body, but the pull of gravity will be slightly less at the top of the mountain than it would be deep in the valley. So if we imagine the moon and the earth, okay, how does gravity on the moon compare to gravity, the force of gravity on the earth? It's less. So a person's weight on earth would be greater than their weight on the moon. Why you could jump on it. What about the mass? Same mass. We look at Jupiter. Why? Yes, because of the larger mass. So, your weight on Jupiter? More. So it will be harder to jump if you were able to stand up. Yes. The larger the planet, the greater the force of gravity. I mean, it's not really size, it's the mass. So the mass on Jupiter, again, same as your mass on Earth. All right, I'm just going to go through this quick. So basically, your mass. Now this, I don't really like this because does your mass? Is that true? Your mass never changes? No, your mass is changing. You guys are growing. Right, your mass is certainly changing. I certainly see Mr. Carey's mass changing.
Oh my God.
What? Just said changing. You're interpreting more into that statement than I meant. But your weight, so I should say your mass doesn't change with location. Your weight does. All right, I'm going to skip this. All right, I will watch those at the end of class. We got to talk about a little bit of density. All right, density. So now we talked about volume, mass. What does it mean if an object is dense? An object has a high density. Now, I'm not talking about like, you know, mentally you're kind of dense. What does it mean in an object? What? You're a tiny bit more and you're correct.
A tiny bit more.
Okay. Yeah, but I'm going to build on why it says it's about, what did you say, Wyatt? Okay. But these two cylinders, hold on. These two cylinders, do they have the same density? They do. But does this have a greater mass? So how is this going to what Wyatt said? He said it's the amount of mass. Just got to add a little statement here. Very close, but not an area. Volume. The amount of matter in a given volume. So if I took equal volumes of these, would they have the same mass? Yes, because they have the same density. Okay? Look, if this one is double the volume of this, what do you think its mass is? Double. What do you think its density is? Yes. All right. So, density is the amount of matter in a given space. Some substances, the molecules are very compact. There's not a lot of space between molecules, and therefore, they have what kind of density? A high density. Other molecules, there's a lot of empty space between them. They have a much lower density. So it's the amount of matter in a given space. And so density is what we call an identifying property. Pure substances at a given temperature have a characteristic density. Aluminum, for example, pure aluminum always has a density at a certain, I think it's 20 degrees Celsius, has a density of 2.7 grams per cubic centimeter. That's the density of aluminum. This is aluminum. So the density of this piece of aluminum, 2.7 grams per cubic centimeter. So if I cut this in half, why would the density be half? No. Why?
But it didn't change the concentration.
That's true, but I didn't. What would I have done to the volume? Decreased by half, but I also decreased the mass by half. And density is actually just a ratio of mass to volume. All right. Density determines also buoyancy, whether or not an object or a liquid floats in another. So less dense objects do what? Float in more dense liquids or gases. So a helium balloon floats, but a balloon you blow up with your lungs does not. Why is that? And it's dense. How does the density of helium compare to the density of atmospheric air? Right, it's less dense, therefore helium balloons float. When you exhale to blow up a balloon, the density of the gases you exhale are more dense than air, and the balloon sinks. If you take an object that's less dense than water and place it in water, what happens? Floats. If it's more dense than water, what if its density is equal to water?
It'll go in the middle.
It'll stay wherever you put it. You put it.
Oh yeah, I made something like that before. It was hard.
But density is an identifying property of a substance, but it does change with temperature. Think about what happens as you heat up a substance to its density.
It liquefies.
What happens to its
It
density?
loses density.
Right. What happens to the molecules? They start to move faster and they start to spread out. And therefore, what happens to density? Lower. Imagine a hot air balloon. As you heat the air in a hot air balloon, it expands, becoming less dense, causing the hot air balloon to float. If you turn down off the flame and the air cools and condenses, then it sinks. So by changing that temperature of the air within the balloon, it can sink or it can float. All right. All right. So you mean like gums? All right. So let's just review now. Density, studying density, calculating density, integrates the things you've just been talking about. Because density is dependent on mass and volume, which we now know how to measure. Because you know how to measure mass and volume of objects, you can then calculate and figure out their density. The simple math formula. Can anyone guess the formula for density? The density of an object equals divided by volume. You got the right factors in there. Mass divided by volume. We want to know how many grams per cubic centimeter. So, volume, the amount of space an object takes up. I'm going to go through this quickly. Formulas we have for volume. Length times width times height. Pi r squared times height. 4/3 pi r cubed. I don't know what that one is. 4/3 pi r cubed. That's the volume of the sphere. All right, mass. Amount of space, matter in an object. Devin, we're writing notes here. Density, the amount of mass in an object.
I'm in an object.
Yeah, we don't have a formula to calculate mass, something we measure directly. Units of volume. What are the units of volume?
Yeah.
Oh, cube.
Yeah.
Unit cube.
Yeah, so like centimeters cubed typically, or
Inches cube.
could be, I mean, you want milliliters, liters. How about mass? Unit of mass. Grams, kilograms, milligrams. What do we use to measure it? Well, if it's a regular shaped object, we can use a ruler and a mathematical formula. If it's a regular shape, we can use a graduated cylinder measure. For mass, we would use a balance. Yeah. So let's put it together. Density. Definition is how compact, how much matter there is, squeezed into a given amount of space. Formula. Density equals mass divided by volume. So can you guess the units? Remember, what we do with numbers, we do with units. So with mass divided by volume, what are the units of mass? Grams, let's say grams. What are the units of volume? Centimeters cubed. You could use grams per centimeter cube or grams per milliliter. So that should make sense because what we're saying is every cubic centimeter of aluminum will have a mass of 2.7 grams. So we don't really use equipment. We calculate this using the other two. No, not yet. So we also, because we have this formula for density, like any equation, you could figure out density if you know what? Mass and volume. What if you know the mass and the density? What if you know the density and the volume? Now, do you know how to do that? Cross multiply, like math is a proportion. It's basic algebra. So if you know 2 out of the 3, you could always find the third by putting it into this proportion and solving for the missing one. All right.
That's a lot of text.
It is. So, osmium is a hard metallic element, the densest substance on Earth. Okay? Cubic centimeter of osmium has more atoms than gold or uranium. Those are also very dense substances. Gold is used as a currency for a couple of reasons. One is that it's very dense, and therefore, if somebody gives you a coin made of gold, you can tell that it's actually gold because it's much more dense than other metals. And so you can tell if you're being ripped off by somebody giving you a piece of aluminum coated in gold or something that just has a gold color because the density would obviously be much different. So to check and see if gold is legitimate, you can calculate the density of an object and compare it to the known density of gold. So the density of gold, pure gold, is 19.3 grams per cubic centimeter. Very dense. Okay? So let's say this. If a man comes in, okay, wants to buy a suit with a gold nugget, okay, the person could look at that gold nugget, find its mass on a balance, say it's 47.9 grams, find its volume, the graduated cylinder. So you tell me, is that actually gold?
Yeah. Yeah, probably.
So figure it out on the bottom of your page. Figure it out. Tell me, is it gold? Figure it out, kid. Figure it out. You got all the information you need.
I got it.
You're fine, man.
Yeah, no, that's wrong.
So I set this up. Density equals mass divided by volume. Substitute in my mass, 47.9 grams. Substitute in my volume, 3 cubic centimeters. Do my division, what do I get?
16.
Slice of pita bread?
16 things per thing. It's things per thing.
15.97 grams per centimeter cube. Is it gold?
No.
It is not. This person is a scammer. Maybe they mixed the gold with another metal. All right, so formula for density. How do we solve for it? We're not done yet. Don't put your notes away yet. Mass divided by volume. So tell me the density. Calculate it right now. What is the density of this cylinder? Yeah, you have to do it. You also will have to do it on your homework that I'm about to give you. What are you doing, Balthazar? You have a single number written down there. Judge not, lest ye be judged. Those that live in glass houses shall not drink so. The pot shall not call the kettle black.
What?
Got all those sayings?
Yes.
So let me show it to you. So volume, first you need to know the volume of the cylinder. You know the formula for a volume of the cylinder? Pi times radius squared times height.
I got it. I did it.
So the volume of the cylinder is 49.5 cubic centimeters. Good. Now I already know they've told me the mass. It is 519.75 grams. How do I find volume?
Mass divided by volume.
Mass divided by volume.
Typical bro moment.
Homework, where's the homework? You guys got to pass it out. Well, there's 2 sides, don't forget.